Praise be to Allah, the cherisher and sustainer of the worlds. I'm Dr. Ramsha Mushtaq, and I take this opportunity from today to discuss the topic normal distribution and central limit theorem under the kind supervision of Professor Dr. Saira Afzal. Quote of the day: believe in yourself. You are braver than you think, more talented than you know, and are capable of more than you can imagine. Today's presentation will include concept and importance of normal distributions, properties and application of normal distributions, the central limit theorem, and recent advances and multiple choice questions. At the end of this presentation, the participants will be able to accurately define the term normal distribution and identify the properties of a normal distribution, understand and classify distributions as symmetric or skewed, and find the area under the standard normal distribution given various z values, and use the central limit theorem to solve problems involving sample means for large samples. Normal distribution is a probability distribution that is symmetric about the mean, showing that data near the mean is more frequent in occurrence than data far from the mean. Normal probability distribution is also regarded as the Gaussian distribution. Normal distribution is the most common type of distribution assumed in the statistical analysis. The normal distribution has two parameters. Number one is mean, and number two is the standard deviation. The characteristics of a normal distribution is mean is 0, standard deviation is 1, skewness is 0, and kurtosis is 3. Normal distribution is one type of symmetrical distribution which occurs when a dividing line produces two mirror images. That is, its shape is same on both sides of a vertical line passing through the center. Physicians often rely on a knowledge of normal limits to classify patients as healthy or otherwise. For example, a serum cholesterol level above 200 milligrams per deciliter is widely regarded as indicating a significantly increased risk for coronary heart disease. An accurate determination of a normal value is of critical importance because the decision may be a matter of life or death, because the physician uses these references to decide what type of treatment to prescribe for a patient. It would be unfortunate if the normal limits were faulty. In that case, some patients might receive an unnecessary treatment, while others might fail to receive a needed treatment. Serum albumin is the chief protein of blood plasma, and for any group of persons, serum albumin concentrations tend to follow a normal distribution. The normal limits for albumin are calculated by adding and subtracting two standard deviations from the mean of a large set of observations obtained from a group of presumably healthy persons. This calculation provides the limits that contain the middle 95%, which is a normal range of observations, but it excludes the remaining 5%, of which 2.5% falls in the lower tail and 2.5% in the upper tail. Extreme observations, those in the tails, are considered unusual and may be regarded as presumptive evidence of a health problem. Normal distribution has three main properties. Number one is it is a bell-shaped curve. The appearance of a symmetrical bell-shaped curve extends infinitely in both directions. It is symmetrical about the mean. Particular internal distribution for area under curve. Whether the mean or standard deviation is large or small, the relative area between any two designated points, that is area under curve, is always the same. It is a theoretical curve. The shape and position is defined by two parameters. Number one is the mean and number two is the standard deviation. Now, understanding the bell-shaped curve, first, most important thing is that the mean, average, median, midpoint, and mode, which is the most frequent observation, are all equal to one another in the normal distribution. highest point on the curve or the top of the bell represents the most probable event in a series of data, its mean, median, and mode in this case, while all other possible occurrences are symmetrically distributed around the mean, creating a downward sloping curve on each side of the peak. The width of a bell curve is determined by a standard deviation. 68% of the data points are within one standard deviation of the mean. 95% of the data is within two standard deviations, and 99.7% of the data points are within three standard deviations of the mean. All normal distributions have a particular internal distribution for the area under the curve. Let us look at the three commonly used points along the abscissa. In the figure, 68.3% of the area is contained within mean plus minus 1 standard deviation, 95.5% within mean plus minus 2 standard deviation, and 99.7% within mean plus minus 3 standard deviation. This fact is sometimes referred to as the empirical rule, a practical method that describes where most of the data in the normal distribution will appear. This means that data falling outside of the three standard deviations, 3 sigma, would signify rare occurrences. Normal distribution is a theoretical distribution defined by two parameters. Number one is the mean, and the number two is the standard deviation. The exponential equation for the normal distribution is y is equal to 1 over sigma square root 2 pi exp into minus 1 over 2 into x minus mu over sigma whole square, where y is the height of the curve for a given value x, exp is the base of the natural logarithm, approximately 2.718, pi is the well-known constant, about 3.14, mu is the population mean, and sigma is the population standard deviation. Some other properties of the normal distribution: the curve is unimodal, that is it has only one mode. The curve is continuous, that is there are no gaps or holes. For each value of x, there is a corresponding value of y. The curve never touches the x-axis. Theoretically, no matter how far in either direction the curve extends, it never meets the x-axis, but gets increasingly closer to it. Each normally distributed variable has its own normal distribution curve, which depends on the values of the variables mean and standard deviation. In figure A, same means but different standard deviations are shown. In figure B, different means but same standard deviations, and in figure C, different means and different standard deviations are shown. Two very important concepts. Number one is skewness and number two is kurtosis. Skewness refers to the degree of symmetry, or more precisely, the degree of lack of symmetry. Distributions or data sets are said to be symmetric if they appear the same on both sides of a central point, whereas kurtosis refers to the proportion of data that is heavy-tailed or light-tailed in comparison with the normal distribution. Kurtosis is used to find the presence of outliers in the data, and it gives the total degree of outliers present. Skewness is used to denote the horizontal pull on the data or the curve's width. It can be positively skewed, in which mean is greater than median and mode, or negatively skewed, in which mode is greater than median and mean. Kurtosis is used to find the vertical pull on the data or the peak's height. It can be positive kurtosis, which is also called leptokurtic, which is light-tailed and steeper top curve, or negative kurtosis, which is platykurtic, heavy-tailed with flatter peak. Now, the standard normal distribution. In practical applications, a table of areas under curve for each variable is required. To simplify this, the standard normal distribution is used. It is a normal distribution with a mean of 0 and a standard deviation of 1. If each data value of a normally distributed random variable x is transformed into a z-score, the result will be the standard normal distribution. In the figure, it is shown that a normal distribution of a random variable x is being transformed into a z-score, and resultantly a standard normal distribution curve is obtained. with mean is equal to 0 and standard deviation is equal to 1. Z value is the number of standard deviations that a particular value x is away from the mean. The formula for finding the Z value is Z is equal to value minus mean divided by standard deviation. Now the area under the standard normal distribution curve, to the left, number 1 is to the left of any Z value. We have to look up the Z value in the table and use the area given. To the right of any Z value, look up the Z value and subtract the area from 1. And between two Z values, look up both Z values and subtract the corresponding areas. This is the Z table to obtain the Z values for corresponding standard deviations and means. Summarizing the normal distribution, this is a curve showing the probability density of cases and proportions of the curve with x bar, which is the mean, at 0, and corresponding standard deviations from the mean and Z scores and T scores. Now the parameters for checking the normality of a normal distribution, number 1 is histogram, number 2 is Pearson's index PI of skewness, and number 3 is the presence of outliers, which is also called as kurtosis. Coming to the central limit theorem, it is the distribution of the means of samples of the same size taken from the same population and their variation about the population mean. This theory states that averages calculated from independent, identically distributed random variables have approximately random normal distributions, regardless of the type of distribution from which the variables are sampled, provided it has finite variance. Sampling distribution of sample means is a distribution obtained by using the means computed from random samples of a specific size taken from a population. Sampling error is the difference between the sample measure and corresponding population measure due to the fact that the sample is not a perfect representation of the population. Sample mean is the mean of the sample means will be the mean of the sample means will be the same as the population mean, whereas the standard deviation of the sample means will be smaller than the standard deviation of the population and will be equal to the population standard deviation divided by square root of the sample size. As the sample size increases, the shape of the distribution of sample means taken with replacement from a population with mean and standard deviation will approach a normal distribution. As previously shown, this distribution will have a mean and a standard deviation. The central limit theorem can be used to answer questions about the sample means in the same manner that the normal distribution can be used to answer questions about individual values. A new formula must be used for the Z values, which is Z is equal to X bar minus mu divided by sigma over square root of N. Coming to the recent updates, McDonald's normal distribution. A 5-parameter distribution called the McDonald normal distribution is defined and studied. The new distribution contains, as special cases, several important distributions discussed in the literature, such as the normal, skew normal, exponentiated normal, beta normal, and Kumar-Swamy normal distributions, among others. For an arbitrary parent cumulative distribution function, CDF, the probability density function, PDF, of the new class of McDonald generalized distributions is defined by the formula, where A, B, and C are greater than 0, and are additional shape parameters which aim to introduce skewness and to vary tail weight, and GX. The class of distributions includes special submodels, the beta generalized for C is equal to 1 and Kumar-Swamy generalized distributions for A is equal to 1. If X is a random variable with density 1, we write X is equal to MCG ABC. The density function will be most tractable when GC, GX, and GX have simple analytical expressions. Central limit theorem, the cornerstone of modern statistics. According to the central limit theorem, the means of a random sample of size n from a population with mean mu and variance sigma square distribute normally with mean mu and variance sigma square over n. Using the central limit theorem, a variety of parametric tests have been developed under assumptions about the parameters that determine the population probability distribution. Compared to non-parametric tests, we do not require any assumptions about the population probability distribution. Parametric tests produce more accurate and precise estimates with higher statistical powers. However, many medical researchers use parametric tests to present their data without knowledge of the contribution of the central limit theorem to the development of such tests. So this review presents the basic concepts of the central limit theorem and its role in binomial distributions and the student's t-test, and provides an example of sampling distribution of small populations. A proof of the central limit theorem is also described with the mathematical concepts required for its near complete understanding. Asymptotic properties of the block type statistics. Extreme value theory is an issue extensively applied in many fields. One of the central points of this theory is the estimation of a positive extreme value index. A bivariate central limit theorem for newly introduced statistics is derived. The new family of semi-parametric estimators for the positive extreme value index is provided. Asymptotic normality of the introduced estimators is proved. It is shown that new estimators have better asymptotic performance comparing with several block type estimators over the whole range of parameters presented in the second order regular variation condition. An application to the estimation of the positive valued extreme value index for several real data sets is provided. Coming to the multiple choice questions. Number 1 is the IQ of a given population is normally distributed with mean is equal to 100 and standard deviation is equal to 15. In this case, the proportion of persons with IQ scores above 130 can be given as a function of total population. A is equal to A 2.5%, B 5%, C 25%, D 50%, and E 99%.
D.
Answer is A 2.5%, as I have described that plus minus 2 standard deviation from mean secures 95% of the values, and the remaining values are in the upper and the lower tail, 2.5% in the upper tail and 2.5% in the lower tail. So this is above 130. So 2.5% values will be in this bracket. Question number 2, assuming that the 25-year-old males have a remaining mean life expectancy of 55 with a standard deviation of 6, the proportion of 25-year-old males to live past 65 years will be A 5.2 minus 5.4 divided by 0.3, B 5.4 minus 5.2 divided by 0.3, C 5.2 minus 0.3 divided by 5.4, D 5.4 minus 0.3 divided by 5.2, E 5.2 minus 0.3 divided by 0.3.
C. B.
Yes, the answer is B. This is the formula that I have told. Z is equal to value minus mean divided by standard deviation, and putting the values in the formula, 5.4 minus 5.2 divided by 0.3 is equal to 0.67. Qualify for a standardized test, candidates must secure the top 10% on a general abilities test. The test has a mean of 200 and a standard deviation of 20. Assuming the test scores are normally distributed, the corresponding Z value is 1.28. The lowest possible score to qualify will be A 200 minus 20 into 1.8, B 200 plus 20 into 1.8, E 200 minus 1.28 into 20, D 200 plus 1.28 into 20, E 200 minus 1.28 divided by 20.
C.
The answer is D, and same formula that we have used in the previous calculation, just rearranging the equation. Putting the values in the formula, 200 plus 1.28 into 20 is equal to 22.5. So the lowest possible score to qualify will be 22.5. The mean birth weight of offspring born to diabetic mothers was significantly higher than offsprings born to mothers without diabetes. The median and mode was calculated for a given sample, which is less than the value of the mean. The most appropriate variety of graphical distribution of this data set will be A, positive kurtosis, B, negative kurtosis, C, positive skewed, D, negative skewed, and E, zero skewed. The answer is C, positive skewed, and as I have told that the mean is greater than median and mode, which is in positive skewness. A researcher wishes to select people in the middle 60% of the population based on blood pressure. If the mean systolic blood pressure is 120 and the standard deviation is 8, considering Z value at 0.84, the upper and lower readings that would qualify the people to participate in the study will be A, 60 plus minus 0.84 into 8, B, 120 plus minus 0.84 into 8, C, 0.84 plus minus 60 into 8, D, 0.84 plus minus 120 into 8, and E, 120 plus minus 60 into 8. Anyone?
B.
Yes, the answer is B. Same formula, we are using the same formula, value minus mean divided by standard deviation, and rearranging the equation, x is equal to mu plus z into sigma, which is 120 plus minus 0.84 into 8, and the answer is upper limit is 126.7 and lower limit is 113.2. The heights of 20-year-old men are approximately normally distributed with a mean of 70 inches and a population standard deviation of 5 inches. A random sample of 15 men is selected, measured, and plotted on a graph. The kurtosis of this data can be A0, B1, C2, D3, and E4. The answer is D, and I have described the properties of normal distribution curve, and which says that the kurtosis of the data is 3. Recent research reports that the children between the ages of 2 and 5 watch an average of 25 hours of television per week, assuming that the variable is normally distributed and standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are normally selected, the probability that the mean of the mean of number of hours they watch television will be greater than 26 hours will be A is equal to 25 minus 26 divided by 3 divided by under root of 20, 26 minus 25 divided by 3 divided by under root of 20, C, 25 minus 26 divided by 20 divided by under root of 3, 26 minus 25 divided by 20 divided by under root of 3, and E, 25 minus 20 divided by 3 divided by under root of 25. So here the clue is the central limit theorem. Central limit theorem is applied because the whole population greater sample size is concerned, and the formula is used x bar minus mu divided by sigma divided by under root of n, and putting the values in the formula we obtain 1.94. The current breast cancer screening guidelines recommend that women who are 50 to 74 years old and are at average risk for breast cancer should get a mammogram every 2 years. However, women at high risk ought to get a mammogram and breast MRI every year starting at the age of 25 to 40. If such a data is required to be represented graphically, the most suited distribution would be A, positive kurtosis, B, negative kurtosis, C, positive skewed, D, negative skewed, and E, zero skewed. The answer is negative skewed because the tail is towards the lower age bracket from 25 to 40. The weights of 18-24-year-old women are normally distributed with a mean of 132 pounds and a standard deviation of 27. The normality of the distribution of weights can be checked by A, pie chart, B, frequency polygon, C, scatter diagram, D, component table, and E, histogram. The answer is E. The normality of the data can be checked with histogram. Last MCQ, the standard IQ test produces normally distributed scores with a mean is equal to 100 and a standard deviation of 15. The medical students are grouped homogeneously by excluding students with IQ scores in either the top or the bottom. The lowest and highest possible IQ scores of students remaining in the class would be A, Z into 15 plus minus 100, B, Z into 100 plus minus 15, C, 15 plus minus 100 into Z, D, 15 plus minus Z into 100, and E, 100 plus minus Z into 15.
B.
Answer is A. The calculation is done by putting the values in the formula. Z is equal to value minus mean divided by standard deviation, and rearranging the equation, we get Z into 15 plus minus 100. This is the key of my MCQs, and thank you very much. Please like and subscribe the YouTube channel, Community Medicine, King Edward Medical University.
Okay, thank you very much. Very nice presentation, Dr. Ramsha. And we are looking forward to more such presentations in future too. Very well done. Allah Hafiz, everyone.
Thank you very much, ma'am.